Just a disclaimer, everyone. I was told to tell you guys this. This presentation is going to be recorded. Okay, so hi, I'm Peter, and I am a PhD candidate presenting my thesis on an intelligent monitoring system for online induction motor fault diagnosis. So let's start with motivation. Why induction motors? As we see here, induction motors have a lot of uses. So in this case, this is this camera. I'm not quite sure. Still. Yeah, I can only control that. This screen is still okay, I guess. Yeah. Okay, so, well, speaking of which, induction motors, they're used in a lot of industries. So here we have a pinion motor mining operation. So it involves in crushing materials for mining. Hey, Dr. Tian, can you hear me?
Yes, pretty good.
Okay, and okay, all right. And also for pumping applications, as we see here. And also very relatively recently, for electric vehicles, induction motors are used as a drivetrain. So because they're used and it's such big business, maintenance is one of the issues regarding induction motors. And the costs of maintenance are in the billions, up to 160% of the initial investment into the motor itself. There are some typical ways to maintain these motors. So there's a run to break, we run it until it fails, or predictive maintenance, where over certain times we would stop the motor and check, make sure if there are any problems. A more efficient method is condition monitoring. So that is actively monitoring the induction motor, like so, so that we can find out when it fails before it will fail, well before it fails, to do more efficient maintenance operations. So as an overview, I start with a background, and I show you guys, I present some issues related to this field and solutions and conclude. So with regards to background, let's look at induction motors themselves. So here is the induction motor. We've got the stator windings, the rotor, and the bearings. And as we can see here, the magnetic field it spins within the stator windings, and that causes the rotor to rotate based on the induced electricity. And so here's a better view of how the induction motors work. And we can see here, rotating is the rotor bars, which is the focus of this work. This work will focus on rotor bar fault detection. And we use electrical current through the stators and also vibration to monitor these induction motors. And so let's look at how data acquisition is done. So generally, we have sensors and signal conditioning for amplification and filtering, and also a data acquisition board that feeds into a computer for processing. Some work, so this is a 2017 work. It uses vibrations monitoring of induction motors, as we see here. And here's a 2019 work that uses current through wired monitoring systems. Let's look at signal processing. So signal processing generally is we take some data, as we see here, this time domain data, and look into its frequency components that are relevant to a fault. Other works show similar things where this is monitoring the startup current of the induction motor, and then you can monitor a frequency with time changes a certain pattern with the startup as a way to indicate the fault induction motor. And there are other frequency components relevant to the fault that can be monitored. Now let's look at the fault diagnosis. Okay, so the bigger picture is with the signal processing, we extract some features, turn it into numbers that represent the fault, and then put it through a soft computing system before we make the diagnosis. So for example, an illustration is something like this. Say these are monitoring indices related to the condition of the motor, and they are somehow calculated to be faulty or healthy. An example is shown here. This is with the support vector machine. We see it divides the states with a line that has the approximate farthest distance across the different states that's being monitored. And here there is a concept of K nearest neighbors where we diagnose a certain condition based on its proximity to certain points of other known conditions. So what are the issues behind these things? Let's look into data acquisition. So in data acquisition, what it looks like in real life when we try to do this in Thunder Bay, this is a motor repair operation down Mahan Electric. And we try to collect data from the motor. These wires are a hazard. And also, their repair operations run the motors with no load, nothing connected. We just power the motor and try to detect issues that way. So many published works do not consider a zero load condition, even though that is practically very useful for our local industry. Similarly, this is the water treatment plant. They opened a panel for us and we monitored the electrical current this way. So this is definitely not a permanent solution. This is just a table that we placed here temporarily. It's definitely would not be safe or viable to be used for practical purposes for their monitoring applications. Now let's look at the issues related to signal processing. The sideband analysis is a really common way to detect faults, but that is easily influenced by gear ratios that are connected to the load, as we can see in this publication here, and they can be confused for a fault when there is no fault. And as we see, it is based on the shaft speed to detect faults. So fault signals can be unreliable. And also in a practical setting, there are, from what we've seen, there are no speed encoders on the motors, like such as pumps. So these methods that depend on speed, we have no way of detecting it without taking out the motor and attaching something to its shaft. So this is a barrier to condition monitoring in practice. And as for fault diagnostics, how do we create a monitoring index? There's no standardized way of doing that. And also the transparency of the system, so how it makes decisions, is not very apparent. So when we do diagnostics, sometimes there's a missed and false alarm. We can't really know why a system would create the incorrect output if we don't have enough transparency. So that is an issue with fault diagnostics in condition monitoring. So the issues are summed up here, and let's look into solutions to these problems. So as far as data acquisition is concerned, the wireless system problem can be solved by using wireless smart sensor systems. So what it essentially is a system where we do the data collection, the signal conditioning, and all the related aspects of getting a good signal and send it wirelessly to a receiver connected to any computing device. It could be a computer, it could be a cell phone, or a tablet. And so let's look into a little bit of the design, how I come about this solution. So for the signal conditioning aspect, you take the sensor output. So we'll say that's an electrical current signal, and then and do some current to voltage conversion or amplification, and filter it so we remove the noise, and we also bias it so that it is compatible with a battery operated system. And basically the design around this involves impedance. impedances. So the impedance of this part of the circuit has to be greater than the impedance of the resistor that the current is flowing into, so we get the majority of our signal flows into the resistor we want to convert the voltage into. Also, the impedance at this point, before the analog to digital converter, it has to be greater than, it has to be within a certain limit of allowable impedances with respect to the rest of the circuit based on the analog to digital converter's specifications. As for the usable bit range of the analog to digital converter, it is based on noise and bandwidth of the application, as we can see here. So results around this are shown as follows. With regards to an external crystal that's attached to time the system, we have these kinds of results. So on top here, we see a 30 parts per million crystal, and the bottom, we see a 10,000 parts per million crystal with the same frequency resolution. Frequency resolution being the sampling frequency over the number of samples. And so in theory, we should be able to see the same frequency components. But actually, because these crystals are not quite, there are differences in the timing for such a system, we can see that we can tell with a good crystal, we can see the difference in frequencies. Whereas a worse crystal, even under similar sampling conditions, we cannot see it. So basically, we can use the top one for fault detection, and the bottom one, it's not practical for our purposes. Now, let's look at the result of the transmitting sensor, so the whole smart sensor unit. As we see here, this is just the outer casing. Internally, it looks like this, where we've got the wireless, the memory, voltage regulation, crystal, microcontroller, and everything within the design is realized here. And the receiver looks like this, where we have a wireless transceiver with a microcontroller and a serial to USB version to connect to a computer. So now let's look at the solutions related to signal processing. Okay, so these are basically the problems: misleading fault signals and a lack of a speed controller. So bigger picture-wise, in signal processing, first of all, we need to extract fault features from the signal. And so basically, we could take a current signal, as we see here, and look at the frequency domain and look at the sidebands, as shown here. And it shows, in this case, it shows a clear difference between a faulty and a healthy condition. But to bring it back, these sidebands are not quite reliable because connected gears can influence the sideband locations, which could mistaken a fault for like a faulty condition for a healthy one. And so a solution with that is to look into different higher frequency harmonics. We can see from this publication that these higher frequencies are more concentrated within the stator and are less, with the stator windings, and are less influenced by a connected load. So the realization of that kind of solution looks like this. So we got the time domain signal again, and a higher harmonic. A fault analysis looks like this, where according to the theory in that publication, we can get these fault frequencies. And proposed in this work is also additional fault frequencies, because we can see a clear relationship of the fault phenomenon with more frequencies than are predicted by the original equation. So now, fundamentally, we can see that this fault frequency related to the current is related to the rotor frequency. The rotor frequency we can determine by vibration, and of course the current we can collect and use these two synergistic. So working together to get us a more accurate result. Okay, and so the synergistic fault detection method looks like this. We use current and vibration to help us determine a stable operating condition for the rotor speed. and then from there we can extract a feature reliably for our diagnosis. So the test setup is symbolically represented like this. So we got 4 sensors, 3 transmitting sensors for 3 phases of current, and 1 sensor for the vibration, wirelessly and connected to a motor, which is connected to a gearbox controlled by magnetic field. The actual picture of that diagram looks like this, and so we got the motor here, coupling, gearbox, and the magnetic clutch load that acts as load. So if we increase the current to the magnetic clutch, we increase the load. And the sensors is one here, a vibration sensor, mounted to the motor just using neodymium magnets. And a current sensor, which we wrap around the lines using a split core current transformer. So this is an entirely non-invasive operation. The motor can still run, and we don't have to stop it to install these kinds of sensors. And also, since the vibration was used to determine the speed, we did extra steps to confirm the vibration really corresponded to speed with a strobe sensor. So this is not part of the smart sensor system, but it was used as an additional verification where we shine a strobe light of a known frequency, and if a certain sticker attached to the shaft appears to be stationary, then we can verify the speed further with an additional sensor. The faults themselves, since we're dealing with rotor bars, they look like this. So inside the motor are the rotors with holes drilled in them. This is one example. We got 5 motors, 2 healthy, and the 3 others have 1, 2, and 3 faults. 3 holes drilled in them as a rotor bar fault. And they are drilled at our local factory at Holland Electric. So let's look into this synergistic analysis a little bit more. With vibration signal, I can generate an analytic signal that tells me the speed with respect to time. So here's the original time domain signal, like the raw data, the g-force with respect to time of the vibration sensor. And these are, this one is the frequency with respect to time, and this is the amplitude of that frequency, corresponding to that frequency with respect to time. And then the bottom here is an amplitude of an unrelated frequency band to show that the majority of the energy did indeed belong to this speed, corresponding to the speed of the rotor. And of course, you can see variations here from the base derived from the vibration data. It also corresponds to small variations that was visible when we use a strobe sensor to also to double check the speed of the motor. And so, of course, this rotor frequency corresponds to slip, and slip is an important quality which we use to do current-based feature extraction. And so let's look into how that speed, what it looks like when we use the speed to find features related to the fault induction motor. So here is the current signal at full load. And here are the corresponding fault features. So these 2 on the top are for comparison, and the bottom one is the proposed fault detection technique. As we see here, we have, these are sidebands. These are the higher frequency harmonics, and this is a generalized method that is used in this work. And we can see here, all these equations have slip in it, which relates to the rotor frequency. And also, in addition, for a 0 load condition. So this is when the shaft does not connect to any load, and it's just running freely. We can still detect similar faults as we can predict. So with this equation and the known slip, we can predict the frequency, and we observe our predicted frequency in the spectrum of the current. Okay, now let's look into solutions related to the 0 load condition and how to turn these extracted features into indexes. So an example of a feature extraction is shown here, as we've seen just a few seconds ago. And the proposed fault index of this work is literally a signal-to-noise ratio analysis. So we take the signal divided by an estimation of the noise, and then we create a number. And then that number, the larger it is, the more severe the fault, in theory. So the results of that fault index looks like this. So we have fault index 1, 2, and 3 with respect to the slip, which is the speed or loading condition related. And so we have, this is the side, based on the sideband analysis, if I created fault indexes for it. And this is the higher harmonic analysis, and this is the proposed analysis. And in addition, the proposed method, we show here the best results, while the upper ones are average results, not chosen or anything. The best results are shown here just to demonstrate the potential of this fault detection technique used in real applications. And we see here, of course, this is all slip related. So the lower the slip, the lower the loading. And here, this one here with the minimum slip, this represents the zero load condition. So this is the issue that we are trying to address for our local industries. With zero loading, we can see here, if we use sideband analysis, we get a misleading signal. So here, a healthy one is confused with a 1-bar fault. So that would have been a false alarm right there. And in other cases, we can see with this method, the 1-bar fault and 2-bar fault are flipped. So it would be a misdiagnosis of the severity of the fault. Whereas the proposed methods, they have a good balance between accuracy and the reliability of the fault index with respect to the actual fault. So the zero load condition is significant for this kind of application. Now, looking at the fault diagnostics, let's address the issue related to the transparency and adaptability of the system with changes in the system. So the bigger picture, given that we have monitoring indexes that represent the fault, now we have to find out, okay, what kind of soft computing system will work for this kind of fault detection. So for example, we have 2 monitoring indexes here, and then they're plotted and to determine a healthy or faulty condition. So what's the solution here? What can we do in a way that is suitable for diagnostic purposes? The method, the solution in this work is with the use of an evolving fuzzy classifier. So a quick diagram is shown here. And basically, we take the fault indices, as we've seen before, feed them into the system, and then we can generate an output where we can trace why the output occurred. We know the reasons behind how it occurred. So some more details in the following slides. So such an evolving system requires a training and a testing process, looking like this. So the purpose of training is to determine the system parameters, the parameters of the system, and then the purpose of testing is use those same parameters to give us our diagnostic output. So let's look into the training. The input, for example, can look like this. And with a clustering algorithm, we can determine the potential of each data point that goes in. So the higher the potential, it indicates a higher concentration of data closely in close proximity to the point with respect to all the other data. With this algorithm, we can determine a potential, that density, without storing memory and data. It can be done recursively. And then the clustering itself is once we determined a point with high enough data density, we can determine the center of what's called a cluster. And then the cluster spread can then be determined based on the number of points closest to that center with this kind of calculation here. And then we project this cluster. So this is one of many clusters, for example, okay, into membership functions. So membership functions just means the degree of belonging of a certain input with respect to a certain quantity. So if it belongs 100%, then you'll get an output of 1. If it belongs less, you'll have somewhere less than 1, but above 0, since these are Gaussian functions, using the center of a cluster and the spread of a cluster as its parameters. Now, the next part of the training is to determine a firing strength and normalization of the output of the membership function. So we take a minimum here and then normalize it to represent the a firing strength of a certain condition in its contribution to the final diagnostic output. To put this in context, let's say we have a rule. We say if something is very small to very large, and something else, the second input, is very small to small, and something and so forth. It can go to infinity theory. This AND operation of our transparent rule to produce our diagnostics is achieved by the minimum function of the membership function outputs. And then here, this is a step to train the parameters. So given our normalized firing strengths, we can determine an output of the system. However, that output of the system depends on certain system parameters that are not known yet. So this is assuming a TSK1 fuzzy inference algorithm. So Takagi, Sugeno, Kang, 1, first order. And so to solve these unknown parameters, we use a known outputs to feed into the system and solve the equation in reverse to determine the system parameters of our fuzzy inference system classification. So now let's look at the results. So given we got the parameters, we can use them and see what gets output. So the results of look like this. So this is the original data that's input into the system. And this is the resulting clusters on the right. As we see here, there's a close resemblance of this with the fault indexes. So the purple meaning the most severe fault, and the green meaning the healthiest condition. And they closely correspond, which it should be, because these are all separate conditions. And also, in addition, I took also the sideband analysis and converted to a fault index, and as well as my own analysis, and input it all to the system. And the resulting system is something like this. We use these membership functions to determine whether the range, so very small to small, is approximately 0 to 0.2, like approximate ranges. And then, based on this, we can do a diagnostics. So, for example, this is a healthy condition, and it follows this path. So, given a certain output, we know the reasons. We know which inputs cause these certain outputs, and then we have a very clear reason of why a system created, why the system output exists. And for example, this is a 1-bar faulted and a 3-bar faulted. We can trace. We know whatever the system outputs, we know why. And this is a very important concept in condition monitoring of transparent diagnostics. And the results. I guess it's not fair to go in detail, but this is the result of the classifier that I propose with respect to some other established classifiers. And in terms of accuracy and in number of clusters and efficiency, it has an overall highest capability in proper diagnostics of the induction curve. Now, let's see what we can conclude from this work. Okay, so with respect to condition monitoring, wireless smart sensors is concluded to be an absolute necessity. It's in most works we have wired sensors, but when we go to real industrial conditions in Thunder Bay, we see that we really need it needs to be wireless. This is unacceptable. It would be dangerous to implement. So these systems are basically a necessity. We really, it's not an extra bonus for practical condition monitoring. For synergistic fault detection, we can conclude that having more data working together gives us a much more accurate result, because we can track the speed, and then we know for sure when we extract a feature, it is under a stable condition and more reliably representative of what we're trying to detect. And so it helps us create reliable fault indices that are corresponding to actual faulted conditions. Now, as far as accurate and transparent diagnostics are concerned, we can conclude that this is knowing how our classifier makes a decision is pretty critical in diagnostics. Say for false alarm or misalarm, if for any reason we have any incorrect output, we can trace back to the reason and determine whether or not the indices we're feeding into it are representative of the fault, and we can adjust accordingly. So it gives us a lot of flexibility to do something like that. Now, in addition to these conclusions, let's look into some future work, and I guess really importantly, contributions and the acknowledgements. Okay, so future work. We actually, in progress right now by my colleague Hiren, we are implementing our sensors in the water treatment plant. And also, a significant avenue of future growth, future work here is energy harvesting of these sensors. So the sensors we developed are strictly battery powered. Having energy harvesting would increase the practicality of smart sensors in use in the industrial environments. As far as signal processing is concerned, looking at even rotor bar faults, a publication here shows that the fault location influences the severity of the fault that can be detected. So addressing these kinds of issues could be a subject of future work. And of course, there are other faults in induction motors, such as stator windings and bearings, which are also very significant faults that occur in industry. And as for fault diagnostics, there are other means to determine the significance of the data being input to the system. And for example, a principal component analysis, where we look at the components of our data which have the biggest variation that has a potential to help us diagnose the induction motor better if we implement these kinds of techniques. Now, contributions. So contribution-wise, there are 2 publications. So there's one in press and one conditionally accepted. IEEE paper is in its final form. And also 2 patents. So one to the Canadian Intellectual Property Office and another one to the US. And we've applied that one and viewed by my supervisor, Dr. Wilson Wong. Now, acknowledgements. So thank you, Dr. Wong. Thank you, Dr. Tian, and Dr. Udin, Dr. Zhou. You guys helped me, and Dr. Tyagi helped me improve this work. And Dr. Christofferson and Natarajan, you guys, your philosophies really influence how I thought and what I thought was important in this work. And the technologists, unfortunately, they may not be here. Jason, Bruce, Kailash, Morgan, they helped with materials greatly. I could not have done the work without them. And also to peers, Dr. Derek Lee and Shaz, they helped, our discussions helped us move the cases forward. Angelo, Gracia, Turker, Rahul, you guys helped with coding and also making the sensor casing. Hiren for continuing the work with the smart sensors in real applications. And Menzar taking the pictures. And Zihao, yes, you too, for your continued work with wireless improvements. And also I acknowledge the City of Thunder Bay, our water treatment plant, for giving us the facilities, and Milhan Electric to give us a real context of what's important in industry. And my supervisor's company, EMAX Systems Inc., and one of his partners, Sunbest Technology Company, for helping us produce our PCBs, and our local hackerspace, home base, for some parts that I could otherwise would have purchased. So that's it for my thesis presentation. Thank you for your time. If you have any questions, feel free to ask.